So one day I met a guy, a real guy, and she presented me a Rubik's Cube. I said, "Oh wow, a Rubik's Cube." And she presented me another Rubik's Cube. And this time, this looks a bit different, and it is, of course. So she asked me what is the relation between the surface area of these two Rubik's cubes. And let's say this is the Rubik's cube A. So for the Rubik's cube A, I have 3 unit squares, 1 2 3, and 3 unit squares here. So it's a 3 by 3 Rubik's cube. So what is the surface area? Well, that is the 6 times, and as it is a 3 by 3 unit squares, we multiply that and we get 3 times 3 is 9, 9 times 6 is 54 unit squares. Pretty neat. Now what about this Rubik's cube? And she tells me that she has made this by removing the corners. So the problem is the surface area of this Rubik's cube greater than the surface area of this Rubik's cube, or it is equal to the surface area of this Rubik's cube, or it is less than the surface area of this Rubik's cube. So for this B Rubik's cube, which I guess is not a Rubik's cube, what is the surface area going to be? Well, it is not a definite geometrical shape, and I wish to count it. So 1 2 3 4 5. Oh, I will lose track. But then she reminds me that this Rubik's cube is essentially made by removing the corners of this Rubik's cube. So, and she presents me some of the corners, like this one. So, essentially, the question is, what happens when I remove a corner of a Rubik's cube? So, before it was here, it had the surface area as before, and assuming that all the corners were intact, it had the surface area as before. So once I remove the corners, what do I do? Once I remove the corner, I remove one, not this surface because this was not visible at that time, 2, and the third surface as well. So I basically remove 3 surfaces. So I basically remove 3 surfaces. Then what else do I do? Well, I basically add 3 surfaces. 1 surface, 2 surface, 3 surfaces. And adding 3 surfaces increases the surface area by 3. So what is the net change? So the change in surface area, SA for short, and this is basically a fancy Greek letter called delta, and that essentially means change in. So what is basically the change in surface area? Every time I remove a cube, I essentially decrease the surface area by 3, but I also increase the surface area by 3 because these 3 surfaces get liberated. So I essentially increase the surface area by 3. I decrease the surface area by 3 and increase the surface area by 3. So that just cancels out, and the change is 0. And essentially when we remove more cubes, we are just multiplying this by the factor. And when we remove 8 cubes, I guess that's the number, yes, 8 cube, we essentially do 0 change. So there is no change in surface area. And so the surface area of this second of V cube is essentially going to be the surface area of A plus the surface area, or the change in surface area. Surface area of A is essentially 54 square units. We calculated right now, and we add nothing to that. So essentially the surface area, or I chose unit squares, so I will keep with the units. So essentially, we don't change the surface area. Every time you remove a corner, you remove 3 surfaces. And in turn, you add 3 surfaces as well. These 3 surfaces. And thus, you don't change the surface area. So I answer the Gaais problem that both the surface area, so the surface area of A is equal to the surface area of B, and she is satisfied and gives me a glass of milk, and I don't like it. So at last, both of them are the same. No one loses anything except for this guy, and she gains it. So we can call her kind of smart guy. I mean, smart guy. So that was a fun problem. Thanks.